this problem, we will be discussing binary tree searching. The problem statement is, given a binary tree and an integer k, you need to check whether a node with data k is present in the tree or not. What we have to do is, we are given a binary tree, that is every node will have at most 2 children, and an integer k value. Let's say k is the target value. What we need to do is, we need to find whether the target node is present in the binary tree or not. That is, we have to search whether the node is present in the binary tree or not. And how is the input going to be given? The input and output are being handled by a main method behind the scenes. So you do not need to implement the main method or any input output here. So we are not expected to write the function for main method or to write the code for main method, that is the input and output. The inputs are sent as arguments to the function you have to implement. So whatever function we have to implement, we will be having the binary tree as an input parameter and also the target k value as a parameter. What we have to do is, we have to implement the function defined in the stub, use the arguments and return the answer based on the return type of the function. We have to return on the basis of whatever the function is expecting us to return. The structure of the tree is given as a reference for you while writing the code. Do not make any modifications to it. So we do not have to change the structure of the binary tree which is given to us, and we do not have to change any of the rest of the stub, otherwise the test cases would fail. So we have to make sure that we are only writing the code which we are allowed to change. Okay, so let's actually try to understand the problem statement using one example. So the input format will be having some lines, n plus 3 lines of code. The first n lines, actually the first line will be containing the number of nodes. So in this sample input, we are given 6 number of nodes. Then the second line contains n space separated integers, that is 4, 6, minus 2, minus 4, minus 2, plus 2. So these are the nodes in the binary tree. And then next n lines will be representing 3 integers, I, L, R, denoting the left child, right child of the ith node respectively. So first node having left child 2, right child 3, second node having left child 4, right child 5, and so on. So in this particular fashion, we are going to get a binary tree. This binary tree which we are getting is given in the explanation part also. So this binary tree is given to us as an input, and if binary tree is given to as an input, we are given the root node of a binary tree. So we are given 4, and we are also given the target k. So k in this case is nothing but 2. So we are given 2 as a target. We need to search whether 2 is present or not. If it is present, we have to return true. If it is not present, we have to return false. So in this particular binary tree, is there any node with value 2? Yes, there is one node with value 2. And what is that node? That node is the rightmost node, actually the last node in this entire binary tree. So since node is present, what we have to print? We have to print true in the sample input as a sample output. So this is the first example. Let's discuss some more examples to get the problem statement more clearly. There can be only one node in the binary tree, that is number of nodes can be from greater than 0 till less than 1000. It means at least there will be one node, or at max there can be 10 is per 3 nodes, less than 10 is per 3 nodes. Values of the nodes will be from minus 10 is per 9 to plus 10 is per 9. That is, it can be anything in an integer range. Similarly, the target can also be anything from an integer range. So if I take one example, if I take an example as a tree having only one node, let's say the node data is 10. The left child is also null, the right child is also null. Obviously, if there is only one node. In this case, if I give you the target as a 10, what will be the answer? You will say true because target is present. But in this case, if I am saying the target is, let's say 20, is 20 present in this entire binary tree? You will say false. No, it is not present. Why? Because root node is also not equal to the target 20. Left child does not have any node. It is null. Right child does not have any node. It is also null. So entire binary tree does not have the target node 20. But what will happen for 10? Since root node is equal to 10, root node is equals to k value, the target value, we will return true. So this is the first corner case, or you can say the most basic test case where there is only one node. Can there be more than one nodes? Yes, obviously there can be more than one nodes. So what if I take 3 nodes? Let me take 3 nodes, 10 having left child 20, 10 having right child 30, and then left child of 20 and right child of 20, similarly left child of 30 and right child of 30 will be null. All of these will be null. So if I am taking three nodes, one root node, one left child, one right child, then if I give you target as either 10 or 20 or 30, what should be the answer? The answer should be true because 10 or 20 or 30 is present. But if I give any other target, maybe 40, maybe 50, any other target, the answer will be false. So now how will you search a target element? So what we can say, if we are present at the root node, what we can say, we are checking whether the root node is equal to the target or not. If not, then maybe the target can be present in the left subtree. If not, the target can be present in the right subtree. So if we are about to search in the entire tree, we have to search in three parts. First is the root node itself. Second part in the entire left subtree. Third part in the entire right subtree. So these three parts we have to search. And if in any of the parts our target is found, we can say return true. Otherwise, we have to return false. So now that we have covered all the cases which can occur, there can be left child present, there can be right child present. It can also happen there is no left child, there is no right child. So now the milestone number 1 is complete. That is, we have understood the problem statement. Now, how we can solve this problem actually? How we can search whether a target is present? See, for this problem, you will be requiring the concepts of tree traversals. So if you do not know how to do tree traversals, maybe using depth first search or maybe using breadth first search, so you have to first get that domain knowledge and then only you can solve this problem. Once you know how to do tree traversals using any of the methods, now let's discuss one of the dry run or one of the explanation using a test case. So if I am taking a larger tree, a little bit larger tree, now that we have taken smaller trees, and if I take a target, let's say the target value is, maybe you can say 70. So target is 70. Is a 70 present in the entire binary tree or not? I can say 70 is present. Yes, it is present. So it should return true. If I will say the target is maybe 65, is a 65 present? No, 65 is not present. So 65 should say no. 70 should say true, but 75 should say 65 should say false. So how can I search? First of all, if I am following DFS traversal, that is depth first search traversal, if I am using DFS, then what I have to do? I have to first ask to the root node whether it is equal to the target node or not, whether it is equal to the target value k or not. So let's say I am now taking k as a 70. Since 10 is not equal to k, now what should I do? I will be making a recursive call to the left subtree, that is there any target node present in the left subtree or not. If it will be, then we are able to search the node. If it is not available, then we are about to search in the right subtree. So you can do the DFS in any fashion. You can do the DFS in pre-order traversal. You can do the DFS in in-order traversal. You can do the DFS in post-order traversal. You can even do the BFS. So you can also do the level order traversal or the breadth first traversal. It is your wish. Whichever approach you are more comfortable in, you can first code that, and then most probably you can have the another approach also. So first of all, target was not equal to the root node. What we are going to search? Left subtree. 20 will also say I am not equal to 70. The target k is 70. So again, search the left subtree. 40 will also say the same thing. There is no tree in the left, that is the left node is null node. It is a null value. So what should we say? The target is not present. False. Same goes for the right child. The target is not present. So answer should be false. Since 40 as well as the left child as well as the right child does not have target, we should return false. So if entire tree, root, left, right, all the three things are not having the data, return false. Same goes for 20, because left child is not having data, right child is not having data 70. So we will return false. That is false, false. It will be giving me false. What will root node say? There is no target present in the left subtree. It might be there in the right subtree. So let's go to the right subtree. 30. It is not equal to target 70. So what should I do now? Go to the left subtree. There is nothing present. Now finally, as soon as I go to the right subtree, I can say the target is present at the root node. And since target is present, I will return true. 30 will also say what? Since the target is present in my right child, I will say return true. Since 10 will also say that target is present in the right subtree, return true. So overall, I am able to say that target 70 is present using the pre-order or in order or post-order traversal. That is a depth first search traversal. So now that we know the approach, and you can maybe try to figure out the instruction manual on yourself by pausing the video. Now let's try to come up with the instruction manual. So that milestone 2 is complete, and now we are jumping on to the milestone number 3. So we are given a, you can say, a recursive function. If we are trying to solve it using DFS, in this recursive function we are expected to return boolean, that is true or false, whether target is present. We are given the root node, the representing the entire tree, and the target, that is k. So what we need to do, first of all, what is the corner case, or you can say the base case of this entire tree? Whenever we are reaching a null node, we can say that target is not present, because we should not compare null data with the target. If you are going to compare null's data with the target, it is going to give you null pointer exception or any other exception. So since we do not want the exception, since we do not want the error, we have to return false, that target is not present. So first of all, if root is null, then return false, that target is not present. Otherwise, if root is not null, then we can compare the data with the target. If root is there, if node is there, so we can compare whether the node's data is equal to the target. So you can use the val variable. If roots val is equal to the target k, so we can say return true, yes, target is present. Because in pre-order, what we do 3 steps. First root node is checked, then second step left subtree is checked, then third step right subtree is checked. So since we are doing pre-order traversal, we will be first checking the root node. If root node is not able to give me the target, then I am now going to search for the left subtree by making a recursive call. So I can say, if target is not present, if the recursive call on binary tree searching, if binary tree searching of root right child on the roots right child, on roots actually left child first, because we are currently making the left subtree call, is giving me true, is returning true, then we will return true, that is target is found. If the left child or the left subtree is having the target node, overall the tree is also having the target node. If let's suppose the target was 60, since 10 will say the target is present in the left subtree, return true. Since 10 is saying target is present in the right subtree, return true. So if target is present in any of the childs, we can return true. Similarly, I will now check for the right subtree. So whether target is present in the right subtree or not. If binary tree searching, that is the recursive function, on roots right child is returning true, we will say overall we will also return true, because we are able to find the target node in our tree. If the target is not present in the root, neither in the left subtree nor in the right subtree, then finally we are going to say return false, target is not found, target search unsuccessful, So this is the last case, whether target is not present, when the target is not present. So now that we have also done the third milestone, that is nothing but coming up with the instruction manual, let's try to discuss the time complexity of this particular approach. So whether we are using a DFS or we are using a BFS, even if you are doing using BFS, the time complexity will remain same and the space complexity will also remain same in worst case. So what we are actually doing, we are traversing on every node. We are going to go to each and every node one by one. And since we are going to go to each and every node one by one, what is the overall time we are going to take? The number of nodes, because one by one these nodes will be pushed into the function call stack. So if I try to show you in terms of function call stack, what would have happened? First 10 would have been pushed, the root node. Then 10 would have called the left subtree, so 20 would have been pushed. 20 would have called the left subtree 40, so 40 would have been pushed. And then we have popped 40 because 40 is returning me false. We have now pushed 60 because 60 will be pushed. So what we can say, are we going into the depth of the binary tree? Whenever we are doing depth first traversal, we are traversing the depth. So at max, how many nodes can be there? It can be equal to the number of nodes in a particular depth, in a particular branch. So worst case, how many nodes can be there in a particular branch? There can be order of n nodes in a skewed binary tree. So overall time complexity, as discussed, it can go linear because it can go to each and every node. Worst case can be target is not present. If we have to search each and every node, it will go linear time complexity. And what about space? Whether you are using DFS, whether you are using BFS, the space complexity will also go linear in worst case due to in recursion, the recursion call stack, because we are using the stack, we are pushing the nodes, we are pushing the root nodes every time when we are making a recursive call. Or even if you are not using recursion, even if you are doing it using level order BFS, still it will take order of n time due to the queue data structure, because in that you have to use queue in order to store all the levels of a particular binary tree. So it will take linear time, linear space in worst case. That's about the time and space complexity. We will be doing the code of binary tree searching. That is, we will be inline expanding the instruction manual which we have. The recursive function binary tree searching have four major steps. First step was the corner case or the base case, that whether the target node is, or you can say the current root node is reaching a null node. In that case, what we have to do, we have to basically return false directly. So how we can check whether the root node is equal to null? If root equal to null, so we can say return false, because it is the base case, because we should not compare the data of a null node with the target node. Or even if we are not comparing the data, we should not also make the left call and the right call from a null node. If we are standing at a null node, we should not make the left call, we should not make the right call. So first thing is a base case. Next thing, pre-order. Since we are doing pre-order traversal, the BFS, or actually the DFS, that is depth first traversal. If root nodes is equals to the target, we should return true first of all. First of all, we should compare with the roots data. So how I can compare with the roots data? If root dot val, because inside the root node class there is the property val. So if root dot val is equal to the target data, which is k, we should return true that target is found. So these are the two corner cases or two standard cases, whether target is not present or whether target is present. So first case was if the trees were empty. Now there will be two recursive calls. First recursive call should be in the left subtree, then recursive call should be in the right subtree. So if I basically run this code till this point, obviously it is going to show me error. Why? Because if none of these if conditions will execute, then I have to return something. So let's try to write the code for return false. Let's try to return false if the target search is unsuccessful. We are not making the recursive call for now. So what will happen if I will run the code for the same input, the sample input? If root node will be equal to target, I will say return true. If root node will be equal to target, I will say return false. Why? Because I am only comparing with the root node. So actually the output we are getting is false, but we have to get true because currently we are searching for 2, but 2 is not present in the root node. We have to search in the entire tree. So we do not have to only and only compare with root node. We have to compare all the nodes in the left subtree, all the nodes in the right subtree. So what I can do now, if the left subtree is having the answer, that is the recursive call binary tree searching on the left subtree root dot left is giving me true. If the left subtree is having the target node, we will return true that yes, target is present. So if I run it again, what will happen? Let's see what will happen. It will do what now? 4 will make the left call to 6. 6 will make the left call to -4. -4 will call the left to null. And since we are reaching null, we will return false, return false, return false, return false. Target 2 was not present. So we will say return false again. But actually answer is true. We should not only call in the left, we should also call in the right subtree. So similarly, I will make the recursive call that root dot right, is it having the target k? If it is giving me true, I will also return true that target is present. Now finally, if I will run the code, let's see that what is happening. So for the sample input, I will be starting from the root node 4. I will be starting from 4. 6 is not equal to target, -4 is not equal to target, then -2 is also not equal to target 2, -2 is not equal to 2, but finally 2 is equal to 2, so return true, and overall tree will return true. So this is the case when there is almost 5 to 6 nodes. But if there is only one node, let's assume there is only one node and Let's assume the one node data is 10 and the first node is having the left child -1, right child -1. That is, the left child and right child does not exist. We have to give -1 if they does not exist. So what will happen if there is only one node? What should be the target? If I pass the target as 10, what should be the answer? Answer should be true because root node is equal to target. So let's see if the target is true or not. Output we are getting is present. Target is giving me true. But if I give the target as 20, what is the answer? Is 20 present in only one node tree? 20 is not present in that tree, so it should give me false. Expected answer is false. So let's see, and it is going to give me false. So now that we are okay with the corner cases when there is only one node or even if there is no nodes, so let's try to submit the code and see if it is going to work for all the bigger test cases. So the code is getting accepted, and let me just bring the code so that we can discuss the time complexity and the space complexity of this approach. This is the particular inline expansion which we have done from the sample test case. So now that we have completed the fourth milestone, that is the code in expansion, that is from the instruction manual, now we are jumping onto the fifth milestone, that is doing the custom test cases dry run and proving the time complexity and proving whether it will work for all test cases or not. So if the root node is null, return false. How much is the time complexity? Constant. Checking whether it is a base case, that is whether it is a null node or not, it is constant time complexity. Checking what is the data of root node, it is also constant. Checking for all nodes in the left subtree, that is making a recursive call in the left subtree, it is order of number of nodes in the left subtree. Same goes for the checking in the right subtree, it is order of number of nodes in the right subtree in worst case. And finally returning false is constant. So what will be the overall time complexity? Overall time complexity will be one node for root plus number of nodes in the left plus number of nodes in the right. So overall time complexity will become linear. And since we are using recursion call stack space, we are going to take linear space also due to recursion stack space getting filled, because we are pushing the functions one on the top of other, and it can happen for a skewed tree. For a almost linked list kind of tree, the space will be almost linear when there is the height of the tree equal to the number of nodes in the tree. So that's the time complexity and the space complexity. But are there any optimizations which we can do in this code? See, you can try to solve it using BFS traversal, that is breadth first traversal, level order traversal, but still it is going to take same time complexity, similar space complexity. The time complexity cannot be optimized from a binary tree. Later on, when you will be learning about binary search tree, BST, what you can do is you can try to optimize the time complexity in a BST by either making a left call or making a right call. So currently this is the most optimized time, most optimized space. One follow-up question which you can take to solve from your end can be, you have to find the number of nodes in a binary tree which have the multiples of 3 or 5, the nodes which is having the value equal to the multiples of 3 and 5. So you have to first come up with the code of this, and then you have to tell me the time and space complexity.